I'm very happy to welcome you for this special lecture of the second Sunday and to welcome Dr. Seetha, who is the Director of Space Science Office of ISRO. I have known her for more than 3 decades when she was doing her PhD with me. After her completing her MSc in physics from the IIT Chennai, she did PhD on a special kind of binary stars called cataclysmic variables. And subsequently, she continued to work on rapidly oscillating chemically peculiar stars. And also, she is very much involved in all the instrumentation aspects of the projects of ISRO, like the previous missions and Chandrayaan, and even some aspects of Mangalyaan, especially the X-ray related instruments. And she is now the project investigator for this ASTROSAT, which is the first satellite of ISRO exclusively dedicated to astrophysics applications. So we look forward to hear more from her about this very special satellite of ISRO.
I started my work or career with optical astronomy, and then because I was in ISRO, I gradually shifted to X-ray astronomy, mainly instrumentation and observations using instruments flown on satellites. So today I'll give a brief about the upcoming astronomy satellite called ASTROSAT. It is due for launch on September 28th, and all the satellite etc. is ready, and it's just getting mated to the launch vehicle. So you will all be probably seeing it on TV soon. Astronomy, as you all know, because you are members of this planetarium, it has been as old as mankind itself, because human beings first observed the skies, they observed the movement of planets, they observed the positions of stars, and that's how the field of astronomy started. So it's one of the oldest sciences. It's mainly due to human curiosity to understand the environment in which we live. Primary goal of astronomy, as in other sciences, is the quest for knowledge. And one aspect of astronomy which I want to bring out here is it's purely observational and theoretical or modeling, because unlike other sciences which you can alter some experiments in lab, you can't do this with astronomy. You have to observe whatever is coming and then try to interpret it and see that that interpretation holds with any further observations and with any further theoretical modeling. So that is the aspect of astronomy which you should, I think, which makes it a little different from observation, experimental physics or chemistry or other sciences. So essentially you need careful, methodical and persistent observations, and those of you who have observed with telescopes will know when I make these 3 points. Okay, so Indian astronomy itself, as you know, has had several what we call Diggajas: Aryabhatta, Brahmagupta, Varahamihira, Bhaskara, Lalla and many others, and they did study about Earth's rotation, study of the sun, solar eclipses, moon and motions of planets. So, and I'm sure you would have heard Shailaja talking about what we are still uncovering about ancient astronomy in India. Many of us have studied in our schools about Copernicus and the heliocentric theory, who proposed the heliocentric theory, and then Tycho Brahe, who actually designed very good instruments and made meticulous observations of various planets and recorded them very carefully That is why I said the first sentence itself, careful, methodical and persistent. So he was the one who methodically recorded all the observations, but he could not interpret those during his lifetime. It was his, it was left to Kepler to interpret the laws of planetary motions based on the observations which Tycho Brahe himself made, and he also added to this. So he evolved these three laws of planetary motion, and but for these laws we wouldn't be having satellites today. So this is where many students also ask me what is the use of the scientific observations we make. Usually science, when it starts with, does not, when we do scientific observations, we don't aim for any application straight away. If it comes, it comes. If it doesn't, it's still pure scientific observations. So to do scientific observations accurately and then use it to interpret is the main source of observational astronomy. Observational astronomy itself started from, as I said, Tycho Brahe and Kepler, and then of course it improved with several people, primarily Galileo Galilei, because he was the one who pointed the telescope and actually saw the planets of the outer moons of the outer planets. And in the country itself, we had this Jantar Mantars, primarily to compile the motions and predict the times when there will be eclipse, times when sun will be crossing, and so on. So these are some of the ancient activities and not so near past activities which contributed to observational astronomy. The first telescope which was used was 4 centimeter for astronomy, and now many of you might have heard about the plans for 30-meter telescope on ground. At present 10-meter telescope is functioning. So the next question is, what do we do why do we go to space for astronomy when we can do so much of astronomy from ground? So many optical telescopes are there, so many radio telescopes are there, so why go to space? As you can see, the electromagnetic spectrum itself extends right from radio all the way to gamma rays. Now, while the emissions from in radio wave bands reach all the way to ground, similarly the emissions from sources in the sky in optical reach all the way to ground. There are some bands of infrared which reach all the way to ground, but wave bands of ultraviolet and X-rays do not reach the ground. Some portions of gamma rays also do not reach the ground except for the high energy gamma rays. So, these wave bands you can access only if you go above a height of at least 150 kilometers. So you need, for UV and X-rays, you need rockets or satellites, and for infrared you will need at least balloons, and also for some portions of gamma rays also you will need balloons. So this is the reason we need to go to space to access certain electromagnetic windows in which many of the astronomical objects emit their radiation. Okay, so importance of space astronomy is to access electromagnetic windows not available from ground. Then one might ask, why fly Hubble Space Telescope? Because Hubble Space Telescope originally was planned to observe in optical wave band. Though the further missions to put in instruments for Hubble Space Telescope have now included infrared, ultraviolet, etc. The reason for this is um, sources in astronomy are so far away that light, when it comes in the form of plane waves when it reaches us. But when it enters the Earth's atmosphere, because of the turbulence of the Earth's atmosphere, it starts becoming non-plane wave, which means it leads to a certain blurring due to atmosphere. Therefore, even if we build the biggest telescopes on ground, we can't achieve the capability, the final capability of the instrument or the telescope, which is called the diffraction limited capability of the telescope, that we cannot achieve from ground, because atmosphere, although it allows optical wave band, it still limits the resolution with which you can observe objects. Now, angular resolution is important where you want to separate two closely spaced objects as separate from each other. For example, if you see with a smaller telescope, you might see a blurring of an object in the sky, and if you see it with a bigger telescope with a finer resolution, you will see it more clear. So that is what is called angular resolution, and that improves when you go outside the effect of atmosphere of the Earth. And so the Hubble Space Telescope was put into space, and it has much better angular resolution even though it is only a 2.34 meter telescope. So the motivation of going to space astronomy is scientific and technological developments, because when we have to put something on a satellite is remotely controlled. Once it is in orbit, it is remotely controlled. Again, you cannot do much of experimentation. So even before you put the experiment on satellite, you have to anticipate what you want to observe, and you want to anticipate what you might observe, because what we know now may be only limited. You have to also anticipate that this object could emit in much faster pulses or something like that if you want to make important discoveries in some of these wavebands. Therefore, when we build instruments, we have to make them, one, rugged, second, space-worthy, third, we have to make them a little more advanced than what we think of now. So that is the reason it leads to several technological developments, especially if you see in the Western countries where the link between industry and scientific communities is very strong. The scientific communities will say, if I want to make a leap in science, I would like a detector to be able to do this, and their industries will do an R&D and develop that kind of detector or instrument, and that is where the technological developments also come in. Take an example. For example, before IRSP-3, even Indian satellites, we always observe mostly for remote sensing or for communication. So for remote sensing satellite, we are often looking at the Earth. Whereas when you have to look at astronomical objects, you have to look at a particular star and point at it for as long as you can. So that improves the satellite's capability for inertial pointing, what we call inertial pointing, and with an accuracy which is much better than earlier, because the fields of view of the astronomical instruments will be rather narrow to cover only one star or one object. So that is how it leads to developments in scientific and technology. And then of course we try to understand the universe better. Again, why look at different wave bands? there are two aspects. The same object might emit in different wavelengths. For example, the sun. The photosphere of the sun is primarily emitting in optical because it is at 6000 degree Kelvin. It emits like a black body, and as according to Wien's law, 6000 degree Kelvin, the peak of the emission is in yellow light. So you can find, this is one way of finding temperature of stars. The peak emission in which it emits gives you the temperature. But the sun, the chromosphere of the sun emits primarily in ultraviolet, and the corona of the sun, which is much hotter and which we still don't know how it gets so hot, that emits primarily in X-rays. So if you want to study the corona of the sun better, it's necessary to study it in X-rays, because all that you study during solar eclipse of the corona in optical may not be sufficient to understand the corona. So that is one aspect. The other is different types of objects might emit in different wavebands. Take for example objects which emit as black bodies. Most of the astronomical objects do emit as black bodies. So stars and galaxies are primarily, they emit in optical waveband, whereas hot stars, that is stars when they are born, they might be very hot, much hotter than say 20,000 Kelvin or so. They might emit in ultraviolet, and that is why we call that the stellar nursery. And then we have emissions much more hotter not necessarily in the thermal aspect, it might also mean equivalent temperature in non-thermal aspect. Those temperatures, if they are of the order of million degree or higher, then you have to study those aspects in X-rays. Otherwise, you will not know about those. And on the other hand, if you come to the cooler regions, you study in infrared or in radio. So this is an image of the sun in X-rays. You can study what is called coronal holes, etc., which you can never study with a optical image. Okay, I talked about ultraviolet stars. So what we call a stellar nursery is nebular regions where new stars are being formed, and Orion Nebula is one of the best examples, because you can see that nebulosity even with your naked eye, and with a grand picture which is taken with, it's a mosaic of, or it's a composite picture of both Hubble and ESO, and it shows hot stars which are bright and which emit in ultraviolet. They also, and then there are nebula which have a lot of dust. This is again a composite picture taken from the Mount Abu Observatory in infrared, and that is superposed on the optical image taken from the CDK telescope. So you can see dust. I don't know if you can see, because for the sake of recording they have made it bright. So you can see dust, and this is called Eagle Nebula. Okay, so and that is the stellar nursery. The main lifetime of the stars are when it emits, like the sun, which you can observe with your naked eye. And then we come to the end stages of stellar life. Stars with masses less than 7 solar mass will end up as white dwarfs. That is, at the end of their life, when the core nuclear energy is exhausted in the core, then the outer layers are thrown off and the center core condenses or collapses as a white dwarf. Thanks. So those are called planetary nebula. You will see the outer layers and the center object as the white dwarf. And this again, when the white dwarf is formed, newly formed, it has temperatures of the order of 100,000 Kelvin. So it can be seen in soft low energy X-rays, ultraviolet, and then the white dwarfs just cool because they have no internal energy, they just cool as black bodies, and then they will cool all the way to temperatures of the order of few thousand Kelvin. That is the coolest white dwarf so far observed. So that depends on that we think leads to an idea of the age of the galaxy. That's an independent measure of age of the galaxy because that is the coolest white dwarf we know in our galaxy. Okay, so when there are stars much higher than 7 solar mass, then they leave behind a neutron star or a black hole, and the outer layers are thrown off as a supernova remnant. The outer layers are seen as a supernova remnant. And this is again a composite picture of Circinus X1, which has a neutron star at the center. The neutron star has been observed with the Chandra telescope. The outer layers of the supernova remnant has been observed with the radio image, and then this is superposed on the optical image. Circinus X1 is an LMXB, low mass X-ray binary, therefore its optical counterpart is fairly faint, and so it's not very dramatic when you see it in the optical image. So let me just give you an example of. So I said there are these X-ray. So what happens to these neutron stars, white dwarfs or black holes? How do we observe them? Actually, if they remain as single neutron stars or black holes, single neutron stars are often observed as radio pulsars, whereas neutron stars which are in binaries can be seen in X-rays as accretion powered pulsars or as cataclysmic variables called intermediate polars, etc. if the white dwarf is the compact object. So there can be binaries where one of the object is a compact object, which could be either a white dwarf, neutron star or a black hole. The white dwarf binaries are called cataclysmic variables, whereas the binaries which have neutron stars and black holes are often referred to as X-ray binaries because they are very bright in X-rays. Now you might ask how bright. They can emit as much as their intrinsic luminosity can be as much as 10 to the power 36 ergs per second. To compare it with sun's luminosity, sun's luminosity is 10 to the power 33 ergs per second. So these can be 1000 times or 100,000 times brighter than the total luminosity of the sun, and that too in X-rays. That is what makes these objects very exotic. So they are much brighter and they emit much higher, they have much higher luminosity. So this luminosity comes due to what is called accretion. That is, there is this optical star which is there as part of this binary. When this optical star expands, or it might emit also as a wind, when the matter from that optical star can cross its Lagrangian point or the first Lagrangian point. Anytime you have a binary, there are equipotentials around it, and there is one equipotential which forms a figure of 8, and the central point is what is called the Lagrangian L1 point. The importance of this L1 point is any material from either of these objects which comes to the L1 point can be attracted by either of them. So in a binary which has a compact object as one of the components, if material goes from this companion star to that L1 point, either in the form of wind or in the form of actual expansion of the star during its evolution, then what will happen is, because the compact objects have so much more gravity, white dwarf has a gravity of 10 to the power 7 centimeter per second squared, which is 10,000 times more than the gravity of Earth. Neutron stars have 10 to the power 14 centimeter per second squared. So this high gravity pulls that matter towards it from the L1 point. So once this matter comes on, it flows in, and then because it has its original angular momentum, it forms a disk, what is called the accretion disk, around this compact object, and as it flows in, due to viscosity of the material itself, it gets heated and the inner layers emit in X-rays, and so the inner layers which are close to the compact object are seen in X-rays. So that is the one which has a luminosity of 10 to the power 36 ergs per second. And when the compact object is a neutron star, the material can actually fall onto the surface. But if the compact object is a black hole, then there is this Schwarzschild radius beyond which you cannot observe. So you observe it till the matter reaches the Schwarzschild radius. The next question you might ask is, okay, so there are these exotic objects, so how many of them are there? As early as 1970s, there were of the order of 700 such objects discovered. Now we know that X-ray binaries are not the only ones which emit in X-rays. There are many other sources. So the brightest of these stars lie in the galactic plane, and these are the X-ray binaries. But you can see above the galactic plane also there are objects which emit in X-rays, and these can also be studied. And now with the ROSAT catalog, ROSAT was an European ESA satellite. There are more than, totally there are more than 70,000 sources, and the brightest of them are of the order of 20,000 sources. So there are enough of these X-ray sources which can be studied. So now let me come back and then tell you about the Indian efforts towards both X-ray astronomy from space and now with ASTROSAT. So the journey so far has been the Aryabhatta, the first satellite which was launched by India, had actually astronomy experiments, which, because of the short lifetime of the satellite, it was an experimental satellite which we couldn't get data. The first set of data which we got was from the SROS series of satellite, on which we had a gamma ray burst experiment. And then the IRS satellite, where we had the Indian X-ray astronomy experiment. This was a joint development by TIFR, Mumbai and ISRO, and that was flown on IRS-P3. These were and then further we had a solar X-ray spectrometer on GSAT-2. All these experiments were what we call piggyback experiments on other satellites. As you know, IRS satellites are meant for remote sensing. GSAT satellites are meant for communication. So if there was mass available, we put one of these experiments, and if the orbit could be conducive for making these observations. The Chandrayaan-1 and the Mars Orbiter mission were the first dedicated missions for lunar and planetary studies. Actually, the ASTROSAT started well before the Chandrayaan-1 mission, but then the developments in the payloads were so large, indigenous developments had to take place, that it has taken a longer time than the other satellites, and they have been flown ahead of ASTROSAT. So, before I go on to ASTROSAT, let me just tell you briefly how we interpret measurements taken from this satellite experiment. Measurements are done in the form of imaging or temporal or timing, spectral and polarization. Polarization in optical is very common, but polarization in X-rays has been done very minimal. Polarization is one thing which we are still attempting to do. So, imaging, as you know, imaging is, if you can take a picture of the object, then you can study the features of the object, you can study the morphology, whether it's a spiral galaxy, whether it's an elliptical galaxy, etc. You can also find the position of a source. So, if you want to resolve two sources to see whether it's a single object or it's actually two or different objects, you have to do very fine angular resolution imaging, and you can also find the position through imaging. When I say position in the sky to know its coordinates. Now next, coming to temporal data, that is time, intensity of the source as a function of time. That is, does the star become brighter and fainter with time or not? So that is what is called temporal data. You can, it is usually measured as counts per a certain integration time, and individual photons are often detected in X-rays, gamma rays, and in the case of ASTROSAT, even in ultraviolet, we are going to detect individual photons and actually count them. So they can be binned into a certain bin of integration time and you can study. So these are used to study rotation period, pulse arrival times, when it arrives, binary periods, flares, outbursts. So just let me show you some pictures. For example, there can be something like a transient event which occurs for a very short time, as short as millisecond, like gamma ray bursts. The intensity profile will show up like this. This is the background. Suddenly you will see the intensity increasing like this. Then you can also see, let me go to the next slide first and then come back to this. You can also see these are, for example, data taken from the IRS-P3 satellite on a micro quasar called GRS 1915. So you can see these pulses which are coming regularly, and it changes its shape with time. June 16th it has this shape, June 19th it has a different shape. So these tell us about how that matter is flowing. This is a black hole binary. How that we can interpret this shape as how that matter flows near the Schwarzschild radius. So now if you fold these kind of, in the case of neutron star, I told you matter flows right onto the surface. So you can actually find if there is a magnetic field on the neutron stars, like a lighthouse, as and when that poles, magnetic poles are seen by us, by the instrument, you can see pulses coming from the neutron star. So you can find the spin period of the neutron star, and just like I showed you those pulses can be folded one on top of the other to find the average pulse period of the neutron star, and then you will get this profile which is called the pulse phase 0 to 1, and it is repeated 1 to 2. 1 to 2 is just a repeat of that 0 to 1 for clarity. So then you can see how the shape looks and how the matter actually flows near the neutron star. And you can see when we separate it in energy, 2 to 4 keV, 5 to 10 keV, etc., the pulse shape looks different. And this tells us from where the emission is coming. Is it coming close to the neutron star, or is it coming higher up in the accretion column? So that is another thing which you can study with the pulse profiles. So you can study rotation periods, pulse arrival times, binary periods, flares, outbursts, etc. So, when I say outbursts, there are things called transients. Many of these black hole binaries are actually transient sources. Normally, they are well below background. There are only 6 X-ray binaries with black hole sources which are persistent. Cygnus X1 is one of them. That means you can observe them anytime. But most of these other sources, there are more than 40, are transient. That means they are below detection level of most instruments. They emit like a background. Suddenly they will brighten up by as much as a factor of 1000, 10,000 or even 100. They might even become the brightest object in the whole galaxy, brightest X-ray object in the whole galaxy. So, they are called soft X-ray transient, and that is the only time you can study these sources. After that, they get back to that quiescent level or their background level, and then they remain quiet for several tens of years. So, when these go into outbursts, they go into outbursts, the rise time is of the order of few days and the decay time is of the order of few months. So, within those few months, you will have to study it. So, it is necessary to catch them when they are as early as possible when they go into outbursts, and then study them continuously for as long as you can detect them. So, if you see it in imaging, how would they look? This will be the region of the sky. It will be nothing different from the background. You can see some bright sources, but this is just a piece of background sky. But then when they go into outbursts, they can become bright, very bright, brighter than these sources for example, but probably less bright than some other sources. So, to catch these sources, you need what is called a monitor to scan the sky and keep looking for which of these sources are outbursting. Okay, then let me come to spectral data. Spectral data is intensity of the source as a function of energy. One thing I have to bring out here is, often when you talk about spectra in optical, you talk about spectral lines and you talk about individual elements. And so, Chandra and XMM Newton have actually done X-ray spectroscopy to the similar level like optical. But often you also have to study what is called the continuum spectrum, which is below the lines. This is not from Chandra or anything, it is from a gas field proportional counter that I have taken this data. So, you will study what is called the continuum, because the continuum tells us what is the underlying process which emits most of the X-rays. Over and above this, there might be lines, and the lines might vary depending on the geometry of the source, because what is absorbed, or it might vary depending on the energy of the line, it might vary. So, fluorescence lines are often emitted in the accretion disk, and those lines you can see. If you can image it you can also do this in different energy bands. So, you can study the emission process, whether it is black body, synchrotron, inverse Compton. The lines will be fluorescence lines, absorption, emission features. You can study cyclotron lines, you can estimate magnetic fields. So, that is all coming from spectral data. Okay, so I talked all about X-ray binaries. Are these the only objects which can emit in X-rays? No. Stars, stellar coronae, just like the sun's corona, other stars' coronae can also emit in X-rays. Star forming regions can emit in ultraviolet and low energy X-rays. Binaries, supernova remnants, galaxies. Active galactic nuclei is another set of objects where accretion is an important process, where actually supermassive black holes at the center of galaxies can attract stars themselves and gobble them up and emit in X-rays. So, active galactic nuclei, clusters of galaxies, matter between galaxies, all these emit in X-rays. So, coming now to the ASTROSAT mission. ASTROSAT is the first dedicated Indian astronomy mission aimed at studying celestial sources. The multi-wavelength studies are in ultraviolet, that is near UV, far UV and limited optical and X-ray regime 0.3 keV to 100 keV. We can do high resolution timing. 10 microsecond is our capability, best capability, which we can do with the large area X-ray counters, and we can do continuous coverage. We can do high resolution imaging of the order of, based on our ground studies, we can go to 1.8 arc second resolution with the ultraviolet telescope, and we can also do X-ray scans of the galactic plane. The satellite has reached Sriharikota and all the spacecraft activities are coming to an end. So, this is how the satellite looks in portion of its integration. This is the soft X-ray telescope I will show, and these are the large X-ray proportional counters, etc. So, now let me go. So, there are actually 6 payloads on this ASTROSAT. There is this ultraviolet telescope, there are 2 of these at the center of the satellite. Then, and there is the soft X-ray telescope which operates in the X-ray. These 2 are the prime imaging instruments. Though limited imaging we can do also with this cadmium zinc telluride and the scanning sky monitor. So, these are the telescopes with optics, and then surrounding them are 3 large proportional counters, X-ray proportional counters, which can observe in 3 to 80 keV, and then you have the scanning sky monitor which monitors the sky for any of these outbursting sources. And apart from these 5 payloads, we have a small payload called the charge particle monitor, which is on the other side of the satellite, which actually is used only to monitor the charge particle background in the orbit. It will be carried on PSLV C30 XL version. It will be put in an orbit of 650 kilometer. The inclination will be less than 6 degree, most likely it will be 6 degree only exactly. Spacecraft mass is around 1510 to 15 kg. The exact mass will be known after filling the fuel, and mission life is of the order of 5 years. So, the scientific niche is simultaneous multi-wavelength observations using a single satellite. Multi-wavelength observations are usually conducted using several spacecrafts and coordinating between spacecraft and ground-based facilities. In this we can do observations in UV and X-rays simultaneously, taking into consideration the observational constraints of the UV telescope, because UV telescope is a little sensitive, and initially we will be taking a lot of precautions which we will slowly relax as time goes by. So, the energy coverage itself, the UV covers visible, near UV and far UV. Unfortunately, we do not have any instrument to cover the extreme UV. And then we have soft X-rays, medium X-rays and hard X-rays right up to 100 kV. These have overlapping regions. So, we can intercompare the spectra etc. achieved from each of these telescopes, each of these instruments, and this instrument is the most sensitive because it has the largest area. The SSM is put separately because it is a scanning instrument. Okay, so just to give you a brief of each individual instrument, we have 2 telescopes, one which covers the near ultraviolet and optical with a beam splitter, the other telescope which covers the far UV, and image resolution, as I said, will be of the order of 1.8 arc second as compared to 6 arc second of Galax, which was a similar instrument flown earlier. These are twin Ritchie-Chrétien telescopes. We have intensified CMOS readouts with a photocathode right in the beginning. and then they are mounted on a cone-like structure, and in order to avoid contamination, the ultraviolet telescope will avoid bright earth, will avoid 12 degree from ram direction, etc., etc. These are some of the precautions we are taking for initial observing. The sensitivity will go to magnitude 20 in 200 seconds. So these are the wavebands, and the importance of this is that we will be imaging in a wide field of half a degree. Then we have large area xenon proportional counters. These are large counters of the order of 1 meter by half a meter across and almost 1 meter in height. There are 3 identical gas filled proportional counters which are covered with a window. So X-rays which impinge inside these counters will undergo photoelectric absorption and emit photoelectrons, which will then be multiplied by gas multiplication and then be detected as electrical charge pulse, which will then be converted to voltage. So there is a lot of electronics which goes behind this proportional counters, and these are filled with inert gases, and the geometric area, as you can see, is of the order of 10,000 square centimeter, and of which effective area is of the order of 8,000 square centimeter. It will be 5 times better compared to RXT, which was a similar instrument flown in 1996, especially in the regions above 20 keV. And because the pressure of the gas is higher in lux PC, we can go all the way to 80 keV coverage. Then we have the soft X-ray telescope, which will be to study the soft X-rays from 0.3 to 8 keV. This has foil mirrors, and these are conical foil mirrors coated, aluminum foil mirrors coated with gold, which has a 2 meter focal length, and this operates on the principle of total internal reflection in X-rays, and it will operate in 0.3 keV to 8 keV is the energy range. This is again an imaging instrument. It's a collaboration of TAFR and University of Leicester. Then finally we have the cadmium zinc telluride detector, which operates from 10 keV to 100 keV. It will extend the energy range right up to 100 keV, and it has solid state detectors called cadmium zinc telluride, and it has an coded aperture mask on top of it. So we can do arc minute kind of resolution imaging of sources, and the lead institution is TAFR in collaboration with VSSC. The scanning sky monitor, as I said, there are 3 numbers. It is mounted on a rotating platform, so it will keep scanning the sky. It has large fields of view. It will keep scanning the sky to locate any outbursting source, either which is known or which is new. So this will operate in 2.5 to 10 keV, and it can detect of the order of 20 milliCrab. Let me just inform you, Crab nebula is one of the standard sources in X-rays. So wherever you see this crab, it's a unit of the intensity of that Crab nebula in X-rays. It has a standard spectrum, e to the power -2 kind of spectrum. It was very much standard till few years back. Now we know that it also varies with more and more sensitive instruments you have. It we found that it does vary, but still the variability is of the order of few tens of %. So we still use it as a standard calibration source for X-ray instruments in the sky. So each of the X-ray instruments will actually observe crab one after another, and also jointly. So scientific goals: periodic and aperiodic chaotic variability, detection of new accreting millisecond binaries, quasi-periodic oscillations which were discovered by the RXTE, but which we will follow up in the high energy range, because that RXTE had good timing resolution only till 20 keV. Then we have high resolution imaging, where we can use the UV and moderate imaging in soft X-rays. We can do broadband spectral measurements all the way from 0.3 kV to 100 kV in X-rays, and we can also get points in the ultraviolet because we have filters, several filters in the ultraviolet. So we can use each of these filters and we can do broadband spectral measurements and X-ray scans. Okay, so what does simultaneous monitoring give? As I told you, there are these sources which have this accretion. Now one doesn't know, there are some processes where we don't know, for example, whether a burst or an increase in emission occurs from the optical companion, or does it first start from the X-ray source and then goes to optical. So one needs to study the timing of these features. So you can identify a particular feature in the light, what is called the light curve, and then see whether that feature repeats in the various wavebands. So for example, this increase in feature for AGN, actually ultraviolet is delayed compared to X-rays. So it comes from probably the inner regions and then goes out into the outer regions. So these kind of things you can study. Similarly, bursts, whether it comes first, it happens first in ultraviolet or it happens first in X-rays can be known. And so you can see the delay, and the delay can be modeled in terms of what is surrounding those active galactic nuclei and so on. Okay, and then we have, for example, multi-wavelength coverage. There are regions, there are sources which actually emit in different wavebands, starting from radio, infrared and X-rays. So if you observe it only in limited waveband, then you might think it is a particular kind of emission like synchrotron. One thing I have to say, I told you the importance of continuum spectrum. Now continuum spectrum can have confusion. Both synchrotron emission, which is due to electrons spiraling around magnetic fields, when they get accelerated, they emit. That is called synchrotron, relativistic electrons especially. And when they emit, the continuum spectrum is in the form of a power law. When I say power law, it means the number of photons decreases as e to the power something. Inverse Compton effect is another way which you can have X-ray emissions. Here actually lower energy photons like infrared photons, when they undergo what is called Compton scattering near relativistic electrons, again they can get upscattered as X-ray photons. So that's why it's called inverse Compton. Usually in Compton you have the other one, down scattering. Here it is inverse Compton. Now the continuum spectrum from both these processes is a power law. So you can't find out whether it's a synchrotron or an inverse Compton unless you have some other thing like independent magnetic field measurement or something else. So if you do multi-wavelength observations, you can by the modeling, because inverse Compton models will give you a different model for the continuum spectrum, synchrotron will give you a different model, and by finding which of the models fit the observations best, that is how you interpret and say that most likely in this source this is what is happening. And then further observations, if they also corroborate this, then that model fits that source. Okay, so and that can vary with time also, the emissions. So you can have different types of emissions at different times. So this is what we hope to get in broadband spectrum. So we will be covering this portion, and we will also be covering this portion of the spectrum. So let me conclude with this is a project where most of the national institutes have already been involved in either the design phase or the actual realization of the experiment, or studies, simulations, etc. So, just in alphabetical order, I have listed the institutes, and we also have a foreign collaboration with Canadian Space Agency for the UV telescope, that is not the telescope part, but the detector and the electronics part, and Leicester University UK for the detector part of the soft X-ray telescope. We hope to have participation of many more Indian universities and research centers with we will be, after the 1 year of observation by the instrument builders using this observatory, we hope to make it open for proposals by Indian researchers. So, people can submit proposals, they will be evaluated based on their scientific merit. You can conduct observations using ASTROSAT. That is our plan. So, the necessary tools etc. to analyze also have to be put together. So, this is one of the observatories which we plan to, one of the Indian satellites which we plan to actually operate in the form of an observatory. And after the from the second year, that will be from the after the first year completion for Indian astronomers. After the completion of the second year after launch, it will also be thrown open to international community. So, there is a certain percentage of time allotted etc. I will not go into it. You will be seeing it in the next 6 months. So often young children ask me what's so important. I feel it's inspiring because this is exploring without having to go there. Exploring your spaces just by using instruments which you have made and observing with it, and the creativity comes in the capability of the human brain to actually interpret those observations in terms of the physics knowledge which you have and say that that object is actually doing this. I think that is what inspires most astronomers, because you are seeing it, all that I told you about binaries, all that is just an artistic impression. That object is a single dot in the sky which may not even be visible with the biggest telescopes, and you are going to say that that is having a black hole, it is actually attracting matter from this, and this is how it is emitting X-rays, and that is the enthusiasm which drives most astronomers, starting from using ground based or space based, all telescopes. So, I wish to acknowledge all the pictures which I took from internet, Wikipedia etc., and of course the ASTROSAT project, and with this I conclude my talk. Thank you.
So thank you very much, Madam. And very shortly, this is going to be another feather in ISRO's cap. So let us wish them the best. Yes. And it's going to be launched very shortly. And we thank you all for your gracious presence and the wonderful questions as usual. And Messrs. Video Hut Productions for the wonderful coverage.